Our second 2021 Mariam Mirzakhani keynote speaker is Dr. Chiara Sabatti. Dr. Sabatti grew up in Italy, where she attended Liceo Classico Arnaldo in Brescia. In 1993, she earned her BS and MS summa cum laude in economics and statistics at the Bocconi University in Milan, Italy. In the same year, she was awarded a Bocconi Fellowship for Advanced Studies. Dr. Sabatti came to Stanford in 1994 to pursue a PhD in statistics and work with Jean Liu on multi-scale Markov chain Monte Carlo, MCMC methods. Between 1998 and 2000, she was a postdoctoral scholar with Neil Risch in the Department of Genetics, also at Stanford. In 2000, she joined the faculty at UCLA in the newly established departments of Human Genetics and Statistics. She received the NSF Career Award in 2003. Until 2011, she was Professor of Human Genetics and Statistics at UCLA, and for part of that time was an associate of the UCLA NASA Institute for Cell Mimetic Space Exploration. Dr. Sabatti is now Professor of Biomedical Data Science and Statistics at Stanford University, a member of BioX and of the Biomedical Informatics Training Program. She is also Associate Director of the Interdisciplinary Major in Mathematical and Computational Science, September 2019 to the present, as well as Associate Chair of Education and Training in BDS, Biomedical Data Science. Dr. Sabatti's awards include the Vesa Cube Award for continuous commitment to the Fiat Lux seminars, the UCLA Career Award, the Statistics Department Teaching Assistant Award at Stanford University. She has also served on many grant review boards, as well as organized technical references in the US and abroad. Please join me in welcoming Dr. Sabatti, who will speak to us about the language of inductive reasoning.
Thank you very much for the kind introduction. And let me see if I can share my screen. Do you see well? Okay, fabulous. Well, I have to thank everybody who has organized this beautiful event and the competition behind it. And I have to congratulate you who have won this prize and have done all of this hard work. And before I dive into the topic for today's discussion, I would like to encourage you to think about what this achievement tells you about yourself and what it tells you about the people around you. Certainly, you should congratulate yourselves and be aware that this is just one of the signs of the fact that you can do many important things. And at the same time, I think that if you got this far, you probably got the help of someone. And I certainly should be grateful to them. But what I want to point your attention to is that people are actually happy to help. As you got somebody's helping you now, maybe just suggesting that you enroll in this competition or coaching you, be aware that all through your life long, you should feel free to ask for help, and people will be much happier to give it to you than you typically tend to guess. At least this is a mistake that I have made in the past of trying to do a bit too many things on my own and underestimate the generosity and the willingness that people have to help. And it's very important as you progress in your life to get as much help as you can in many different areas. So please continue to that on that. Of course, the other thing that we want to reflect upon today is the power of mathematics, and the talk you have just heard gives you a wonderful overview of one domain that maybe you had not considered before, where really mathematics has crucial roles. And I'll try to give you another perspective on the same topic. We have been sharing a little bit about our journey. So let me share you a little bit about mine and how I started off from a little village in northern Italy. I did not have I did not have to face any major problems in my life long. I've actually have been a pretty happy person and pretty lucky in how things have gone. But I can tell you that where I grew up, the idea of being a scientist was totally foreign. If you had to tell me that I would be a university professor or a scientist, I would never have believed you. I thought that these were people that lived in another planet and had a completely different experience. So I want to urge you to keep in mind this as a possible career, even if it sounds bizarre to you now. It's actually a very fun one and rewarding one, and we do need your help. Okay, so to get to the point of the talk, let's consider a question like this one that is, unfortunately very actual to our situation nowadays. Suppose we have a new treatment and we have some claims that this treatment is effective against COVID-19. How would we go about deciding if this statement is true or not? I think we all get the idea that, we will get some data and use this data to decide. But I want to push you a little bit harder and think, first of all, it's not very immediate to define what does it mean to be effective. And secondly, what does it mean to really conclude some statement from data? So let's take one question at a time. And first, let's look at what does it mean to be effective. Most people, fortunately, even if you do not do anything, they will eventually get better from COVID-19. So in order to distinguish the possible effect of this particular treatment, we have, first of all, to try to define specifically what we mean with success. So we might define an outcome like there's no fever and no respiratory difficulties within 2 days of taking the medicine. Another outcome may be if you take this medicine, you will not be hospitalized. So you'll just have to make some decision about how you're going to frame, which particular frame you're going to use to look at the world. Then, of course, we do not expect the treatment, even if it is effective, to work equally in every person. So we're going to make a statement of the time, your chances of getting better in 2 days increases of this much if you take the treatment or not. And what I have just said highlight the fact that, we need to make a comparative statement. We have to compare how well you do on the treatment versus how well you do without the treatment or with the placebo. So,
and I'm sorry, Professor Sabatti, you're doing great. I see your title slide. Have you gone past that yet, or?
Yes, quite a bit.
Okay.
You do not see my title slide moving?
I only see the first, I see the title that says the language of inductive reasoning. Oh, now I see something. Now it says, how can I learn from data?
Do you see it, the entire screen?
Yeah, now I see
only...
it. Yes. Okay, it's working now.
It looks okay now?
Yes.
All right, so let's say that we use this specific definition of what is success. That is, a patient has no fever and no respiratory difficulties 2 days after taking the medicine. And what we're going to do is that we might want to look at the proportion of cases in which this event is true. And for simplicity, let's say that we know what is the proportion of cases where this event is true if you have no treatment. And what we want to do is we want to discover if the treatment, if taking this medicine gives you an improvement. Now, if you can see this figure, that I have a rich portrait of Hume. Hume was a philosopher who made some rather dramatic statements. In particular, he emphasized that this business that we have in mind of possibly learning from data, it's really rather tricky. There is a picture of Hume and a picture of swans. One famous statement of Hume is that no matter how many white swans we have seen, we can never conclude that all swans are white. What he points us, it's what is known as induction paradox. The idea that no matter how many specific instances of something you can see, it's very difficult, in fact, it's impossible logically, to go from a series of specific instances to an overall conclusion. So we want to make a general statement that says all swans are white, and Hume says you can never make these general statements simply starting from a series of specific observations. So if you want, there are two ways of reasoning that we often use. One, it's called deductive, and it's typically actually the one that we are more trained to do in mathematics. In deductive reasoning, you maybe apply a set of transformation or simplifications that allow you to show some truth that it's implicit from the beginning. You have started from some general statements and you work with them till you can say, if I make all of this assumption, then this thing is true. In the case of induction, instead, you make a series of specific observations, and from these specific observations, you try to infer a general statement. This is typically what we do in life, okay? When we don't have a professional hat on and we just observe how people behave in a certain environment. We observe what happens if I turn on the water and I turn the tap in one direction versus the other one. When does it become hot and when it becomes out cold? We just have a series of experiences, and from these experiences, we gather general statements. What Hume says is that this way of reasoning that we use all the time, it's logically flawed. We cannot actually see it happen. We cannot really make a solid conclusion. And this is somewhat troubling. So what I want to do with you today is to explore another way in which to explore one possible way of resolving this paradox. And it's one opportunity to show the power of mathematics and the connection between mathematics and science. Maybe you have heard this sentence that it's attributed to Galilei Galilei that says that the universe is written in the language of mathematics. So we often think of course, mathematics is important for every science because we use mathematical language to model whatever is it that we think it's happening in chemistry, in physics, and even in biology. What I want to point your attention to is that mathematics is important for science, not only because it provides a modeling tool for everything that goes on in science, but also because it provides us with a language for induction, a way in which we can, even if we cannot logically prove some general statement from a series of particular, we can be specific about what does it mean to learn from data, and we can be quantitatively sound about it. And this is the area of probability and statistics, which is the area where I work in. So today I would like to very briefly introduce you to 3 different definitions of probability and get a sense of how notions of probability and statistics can help us overcome the induction paradox. So what is probability? Presumably you have seen a definition like this one. In some cases, we can enumerate all the simple events, the simple possible outcome for an experiment, and we know that they all have the same probability, whatever that means. Think of the case of a deck of cards that it's appropriately shuffled, and you randomly ask somebody to randomly select one card out of the deck. Then we can think that the selection of every single card has the same chance of becoming true. And then we're going to define the probability of any event as the number of cases that satisfy the event over the number of possible cases. So if I consider an event like the card is a number strictly less than 4, to define the probability of this event, I'm going to say, well, how many cards satisfy this particular property? There are 3 clubs that satisfy this property, 3 spades, 3 hearts, and so on. So I have a total of 12 cards that I could extract that have a number less than 4, strictly less than 4, and I have 52 possible cards to extract. So the probability of this event is 12 over 52. And this is maybe the probability definition that you have seen before. There are some properties that goes with this probability definition. And let's say, for example, the probability is always a number between 0 and 1. Of course, if it is a ratio of the number of possible cases that satisfy a property over the number of all possible cases, we expect this to be, we see that this is going to be a number that is more than 1 and it's positive. We also see that if I look at the probability of the event that describe every possible case, this is going to be 1 because it's going to be the ratio of 2 things that are the same. Or if I look at 2 events that are incompatible, so they cannot be true at the same time, the probability that either one of them is true, or what we use using the language of set theory, we call this the probability of the union of the 2 events, is equal to the sum of the probability of the 2 events. So if I want to look at the probability that a card is a number less than 4, or the card is a queen, I simply have to count the number of simple events that satisfy the first condition and the second condition and divide by the total number of possible events. And I can see that it's going to be a sum. Here is a notion that maybe you are not so familiar with, and it's very important in science, that one of conditional probability. I say that I condition on an event B when I intend to restrict my attention only to the cases where B is true. So when I condition on event B, this becomes my entire universe. I assume that B is true, and I'm going to look at the probability of another event given that B is true. The symbology that we use is probability of A given B, and this is defined as the number of cases in which both A and B occur over the number of cases where B occur. So let's consider a very simple example where we say A is the event that is true if the card that I choose has a number that is strictly less than 4, and B is the event that it's true if the card is not a figure. Then the probability of A given B is equal to the number of cases where both A and B are true, which is just equal to the number of cases where the card is less than 4, because those ones are not a figure, over all the possible cases that this time have decreased to 40. Okay, so I did these excursions for us to get back to our problem of, we want to evaluate if the medicine is useful or not. And we said we're going to evaluate if the medicine is useful or not, evaluating the probability with which a person gets better within 2 days. Well, the definition I have given you for probability doesn't seem to help us very much. What are the equiprobable simple events that I have to count? I am thinking that the medicine does something, right? So the getting better or not getting better do not have the same chance. What is it that I'm going to count to put in the denominator and in the numerator? Even the definition of probability here is rather funny. So let's take a step backwards, or let's reflect on this a little bit. So we can think about getting better or not getting better as the outcome of a coin flip. And let's say we have a coin that has probability P of heads. And let Xn be the number of heads that I count out on n tosses. So I'm imagining to toss the coin n times, and I'm going to count how many times I get a head. This number is what we call a random number. It's a random outcome. A priori, I don't know how many times I will see a head. And the possible values for this xn are numbers that go between 0 and n. And for each of them, if we assume that the probability of heads is p, and if we assume that once I toss the coin one time, I do not change in any way the probability, the outcome of the next tosses, I can evaluate the probability of all of these outcomes. For example, if I look at the probability with which the total number of successes is equal to n, that is equal to p to the n. Now, there is a very interesting result that is due to Bernoulli that says, okay, let's take the ratio between the total number of successes out of n trial and the total number of trials I have done n. So this is the empirical frequency of success. And if I let the number of trials go to infinity, that is, if I keep tossing the coin over and over again and recording what is the empirical frequencies of success, this is going to converge to the value p. So remember, p is my probability of heads, which could be 1/2, but it could be any other possible value. If I record the frequencies of successes, as the number of experiments grows to infinity, this is going to go to p. So in fact, we can use this as a definition of probability and as the limit of the frequency of success. And this makes sense in our context. We could say, yes, indeed, our experiment consisting checking in one person, does this person get better after 2 days or not? If I record this across very many people, as the number of people that I analyze increases, I'm going to have a better estimate of the number of successes. So does this help us with the induction paradox of Hume? We never know exactly what is the probability with which one individual will get better after 2 days, because this is a statement that refers to all possible patients in the past, in the future, in every possible conditions. But if we have an experiment large enough, if I look at a large enough number of subjects and I record how many of them get better after 2 days, what we have just described gives us a sense of where this probability may be. And what is interesting is that not only gives us a guess, but it tells us that if the number of people I look at goes to infinity, this guess becomes better and better. Still, there is some circularity, right? We need to define these probabilities as the limit of the frequency. Then what are we really learning? If the probability is the limit of the frequency and we look at frequencies to learn the probability, there is something going around that it's still kind of fishy, and you can still argue that Hume has a point. So let me conclude with a third way of looking at probability and another way of overcoming this induction paradox. This notion of probability, it's known as subjective probability, and I'm pretty sure that you have not seen it because it's not something that we encounter very early in our studies. This notion says, look, probability, you can think of it as the price that you are ready to pay to participate in a bet that gives you a payoff of 1 if the event turns out to be true, and a payoff of 0 if the event turns out to be false. So here is a little table. We look at what are the possible states of the world after you have done your experiment. A could be true or A could be false. So your card could be a number strictly less than 4, or your card could not be, could be a number that is bigger than 4 or a figure. The price of the bet, if you think of it in terms of your gain profile, if you participate in this bet, you pay a price PA. So no matter what is the state of the world, to participate in this game, you have a negative gain of minus PA minus PA. Now let's see what is the outcome of your bet. So depending on if A is true, you are going to receive back 1. And if A is false, you are going to receive back 0. So if I look at the total gain profile that you have under each condition, if A is true, you are going to gain 1 minus PA. And if A is false, you're just going to be left with minus PA. If we take this definition, we are saying that probability is subjective. Two people could be ready to participate in bets and pay different price. So we might think, oh my goodness, now everything, we are going to go wishy-washy, and instead of being reasoning mathematicians, we are just going to go by feeling, and my gut tells me to do this, your gut tells you to do that. And there is a little bit of that, but not too much, because what we're going to ask is that while everyone is entitled to their evaluation, we are going to ask to everyone to be coherent, to be rational. That is, you cannot give evaluations of probability, you cannot choose prices such that it wouldn't be possible for you to always make a strictly positive gain or a strictly negative one. So let's look, for example, at the same table we've seen before. What I have, when I just reported here, what is your total gain? Your total gain is 1 minus PA if A is true, and it's minus PA if A is false. What we're going to require is that this total gain cannot be always strictly positive or always strictly negative. And if you look at these numbers, you see that for this to be true, it has to be that PA has to be between 0 and 1, right? Because if I had a PA negative, then this will be a number bigger than 1. This one will be a positive number. So I will be always gaining. And if PA was smaller than 1, if PA was bigger than 1, then I would have always a negative gain. So the nice thing is that if you ask people to be rational, in fact, we can reprove all of those properties that define probability, even with this definition. Why do I bother to introduce to you this bizarre subjective notion of probability? Well, because this unlocks for us another way of looking at the induction paradox. It tells us you can use probability actually to describe your degree of knowledge. Probability doesn't have to refer only to something that is truly random that happens in reality. Probability can be the instrument you use to say how sure you are of something, how strong is your information with regard to this possible event. And if you do this, then instead of having the situation where learning by in inductive fashion means that you start from a series of special particular observation and you try to make a general statement, you can say, well, I start with a general statement. And what data is going to do for me is to make this general statement more precise. This is the key behind Bayesian inference. And Bayesian inference says, well, start with a statement that expresses your degree, your knowledge so far. And your knowledge may be rather imprecise. So you can use a probability to describe how sure you are of one possible outcome of one theory or not. Then you collect data and you use this data to revise your current knowledge. So you're going to again to use a probability, but this probability is going to express your increased amount of knowledge on the same theory. So let's look at our problem where we want to learn about the effectiveness of this drug. And P is the probability with which a patient gets better within 2 days after taking the drug, and P is what we would like to learn. We have seen that we could collect data on some N patients, see how many of them get better, and we could use these empirical frequencies to get some sense of what is the value of P, but that still doesn't quite satisfy humans. No, now let's look at another approach here. Let's say that at the very beginning, we express our level of knowledge saying that P is a number that has to be between 0 and 1, and I really don't know what it is. So I'm going to say that for me, it's equally likely to be any number between 0 and 1. So I'm making a statement on P, say, I don't know what it is. It could be any number between 0 and 1. And in fact, I believe it's equally likely to be any of these possible values. With some mathematics, you would see that this is equivalent to say that if you have to make one guess, your guess for P would be 1/2. Then let's imagine that we collect data and we have N patients who are given the drug. We count how many of them get better in 2 days. And again, with some mathematics, you could write out this general formula that says the probability that if you look at N patients, the number xn of those that get better in 2 days is equal to any specific number x is equal to this little expression that is known as binomial formula. So we have our prior ideas, we look at data, and now we use this to update our prior idea. The way we do it is using those conditional probability that I quickly introduced for you a little bit ago. Remember, we had here a prior probability evaluation on my theory. Then I get the data, and with the data, I get a posterior evaluation of the probability of my theory given the data. So we are going to update our beliefs on P, and following some mathematical work that is based on these conditional probabilities and on what I have stated here and the probability of my data, I revise my notion. If I start with this particular prior, I collect this data. The logical way of revising my notion is that my posterior guess for what is the probability of the drug to be effective is 1 over plus x over 2 plus n. So originally I thought that the chances for one person that took the drug to get better in 2 days is 1/2. After I have observed that X people out of N get better in 2 days, this is how my chances change. You can see that as N becomes bigger, X over N, it's really going to be the leading term of this expression. So as your sample size increases, your guess for what is the probability of getting better in 2 days becomes closer and closer to the sample frequency. But this time, you can respond to Hume that everything is taken care of because you have not just bootstrapped this out of nothing. You started with some general ideas and you have used the data to revise your idea. So let me conclude telling you why I love probability and statistics. I love them because I think that the world is not black and white. And sometimes people object to mathematics saying, oh, you know, you mathematicians, you tend to see things are right or wrong, and that it's so different from the complexity of the real world. You are cold-blooded, you don't see all of the suffering that goes through me, and also it's reductive, okay? I agree with that the world is not black and white, and we cannot try to force it in being black and white. I don't agree with the mathematics being a reductive way of looking at things. And I want to make a strong statement that while I believe that the world is not black and white, this is very different from saying that everything goes. It's not, we cannot just allow ourselves to say any kind of things, make any type of conclusion. There are things that are not coherent, there are things that are not rational, there are things that are not helpful, that there are things that are not true. And probability and statistics give us a language to navigate uncertainty and imperfect knowledge without losing coherence and rationality. So they really help us to translate this power of thinking and clarity that mathematics gives us, to translate it to domains where it's not possible to clearly say right or wrong from the very beginning. But this doesn't mean that we cannot be precise of how much we know and how much we do not know. So you guys are brilliant mathematicians. You'll become even better mathematicians if you stick to it. And I think it's really my invitation to you. It's to continue using these incredible skills that you have and cultivate them so that you can help everyone in science, in engineering, whatever domain of life we are in. We do need the rationality and the clarity of thinking that mathematics helps you develop. And we do need this language of mathematics in medicine, for example, which is the domain where I work the most. So thank you, and thank you for your attention. And if you have any questions, I will be very happy to answer it.
Okay, great. Well, thank you for that, Professor Sabatti. I use probability a good amount in my work, but I don't really get to think about these foundational issues as much. So thank you for explaining. I do encourage the girls, if you have questions for Professor Sabatti, go ahead and type it in the Q&A box, or the chat box is okay too. But in the meantime, I'll ask a question or two. Your talk was mostly focusing on the foundational questions, but I know you also do work on applications, for example, applications to genetics. I wonder if you would like to say a word about how do you use statistics to analyze questions in genetics?
Sure. Thank you for that questions. So actually, mathematics and statistics and probability and genetics go hand in hand from the very beginning. People started talking about how we inherit characteristics from our parents before the DNA was discovered. So we actually did not have a mechanism for inheritance, but people started using mathematical models and statistical models to think about how that might be. So the very first way in which genetics and mathematics intersect is that mathematics actually provides the tools to do the modelings of what could possibly happen. The question that I address the most often in my research, it's actually nowadays trying to identify which portion of the genomes are associated with traits of interest. So say some of us are taller, some of us are shorter, some of that has to do with genetics. Which portion of my DNA is important to determine my height? What people do is to collect a lot of data on heights of individuals, what their DNA variations are at a number of different loci across the genome, and try to find correlations between taller people and variation at some specific areas in the genome. Now, you can see that the data is going to be noise. Your height is not going to be uniquely determined by any particular genetic variation. So you are going to use statistics to sift through the variability and to identify possible correlations. But most importantly, you're actually going to use statistics to separate the correlations that are likely to be important from those that are likely to be spurious. What happens not only in genetics, but in very, very many domains of science nowadays, is that we have so much data and we can look for so many possible correlations that we always find something that correlates with something else. And it really requires a lot of acuity to separate those correlations that are likely to be scientifically meaningful from those that are only spurious. And reasoning of probability type are fundamental in doing this. I don't know what you read, but there is a lot of discussion out there about lack of reproducibility in science, lack of reproducibility of the findings in psychology, for example, has been in the popular media a lot. But even, fundamental things as cancer treatments, there have been some of the most acclaimed studies in cancer treatments that have not been replicable. And lots of this has to do with the fact that we look around so many possible associations, it becomes quite challenging to distinguish those that are meaningful from those that are not. And probability and statistics can help a lot from that respect.
Okay, great. Well, you must have read my mind, because my next question was going to be exactly about the so-called reproducibility crisis and what statisticians can do to address it. But I think you well.
Well, let me expand on that and then a little bit. I try to introduce you to this Bayesian way of thinking. And you can think about the reproducibility crisis in one way, using this Bayesian paradigm and say, okay, some of these things that are not reproducible are very surprising. So let's say we look at the drug. How are drugs discovered? Mainly by experience, right? You have a library of very many compounds, and you test each of these compounds against some cells in a petri dish and see if any of these compounds does something. You start from thousands of compounds that are not selected in any meaningful way. They're just, whatever chemistry has provided us, what the environment is around us, most of them fungi to start with. The chances that any of them has any functional effect on the disease that you're looking at are a priori very small. There's no reason why they should. So if you see an effect, you shouldn't immediately believe the effect. You should modify what the data tells you on the hindsight of what is your prior knowledge, that the chances that this matter, that this is going to work, are very small. So if you start with, the chances that this particular compound is going to work are very small, you're going to require a lot of evidence from your data to convince yourself that it actually does something. And one way of looking at the reproducibility crisis is that we look for association all over the world. And, if we are objective about it, when we say, well, the chances that these two things are actually related is a priori very small, because I don't have any motivation to look at these particular two variables together. And so I should be very careful in asking from my data a very strong evidence of their association before I get excited. Does that help?
Totally makes sense. Thank you for explaining that. We received a question in the chat box, and I'll read it. From the foundations of inductive inference, how do we apply them for machine learning?
So thank you for that question. Machine learning is used today to describe learning from data. The machine has to do with the fact that we use computers to do the computations, but by and large, what machine learning is to say, I have these data sets. Can I identify patterns in this data set that I can use to make prediction in new data that I will observe? So for example, I might look at many CVs and how many of these the people for each of the person that is associated to a CV, how successful they were in one particular job, and then try to learn what are the characteristics of a CV of a successful person, so that next time that the CV comes around and I have to make a decision, should I interview this person or not, I can put the CV in the algorithm, and the algorithm will tell me the probability that this person is going to be successful. I estimate it to be this much. So first of all of these algorithms are built using probability, a probabilistic framework. So you need to be able to talk about probability of the data in order to build this algorithm. Then what is actually very important from a user standpoint, and what we don't always succeed in communicating, is that all of these algorithms don't give me an answer that is absolutely correct. Okay, the answer comes with some error. And so there is a performance matrix of how well these algorithms do. We need to be able to communicate the uncertainty of our predictions. And to communicate the uncertainty of our prediction, again, we have to fall back to this language of probability. Maybe connected to reproducibility crisis, but slightly different. It's another phenomenon that people noticed with the widespread application of machine learning. Sometimes you detect some associations that seem to be useful and predictive, but then don't hold up over time. So there was an article published in the Proceeding of the National Academy of Science that by looking at Facebook profiles of individuals, noticed that if you liked curly fries, you are likely to have higher IQ than not. So that in fact, liking curly fries was a good predictor of your IQ. And it was true in the particular data set that these people looked at. And it was true quite substantially. You know, you can sometimes make some silly mistakes and detect associations that are not there at all, but that one was there. But you can probably agree with me that this is not going to be a causal association, right? And there's not some mechanism in your brain that makes you like curly fries and having a high IQ at the same time. What was going on is that in this particular group, somebody who, you know, was a geek, particularly intelligent or not, and had intelligent friends, discovered curly fries and communicating the liking of curly fries to his friends or her friends and whoever was following their very intelligent conversations. And so this group of intelligent people ended up liking curly fries. And if you were not such a high IQ individual member of that group, you didn't got the curly fried bag. Now, this prediction, that this association that was detected with machine learning, that the machine learning would use to predict IQ levels in other individuals, would not be robust. So if you move to another population that has never heard of curly fries will not be a good predictor of your IQ. So we again use probability and statistics to try to identify which predictions are more robust and how can we develop algorithms that give us robust prediction and, you know, very crucially nowadays, that don't generate or perpetuate biases that are in our data. You know, some of my colleagues were involved in the publication of an algorithm, of a paper that described how if you use some currently used algorithm, you can prove an association in your data between being a woman and a homemaker, just as a man is a computer programmer. So a man stays to computer programmer, as woman stays to homemaker. Those algorithms have detected something that, you know, it is true. If you look at homemakers, they are prevalently females. And if you look at computer programmers nowadays, they're prevalently male. Yet there is really nothing that makes a good there's no requirement for you to be a male to be a good computer programmer, or a woman to be a homemaker, really. It's just what's out there. So if you use machine learning to analyze the data, you'll get this association. You'll think that it's predictive. You want to make sure that the fact that it describes what's happening right now, doesn't become normative, so that you are not going to ever hire any woman in the position of computer programmer because you suddenly think that you need to be a male to do that.
Okay, makes a lot of sense. Yes, I was hoping you would give me a good reason to eat more curly fries, but anyway, we have another question. This is from a student, Ananya, and I'll read it. It says, more generally, how can mathematics be used in medicine and biological research? What are some examples outside of genetics, and what kind of math can be used?
So statistics is used all the time to evaluate the effectiveness of drugs, to decide if a vaccine does its job or not. There is another kind of mathematics that it's more connected to modeling, that it's used in the development of in bioengineering and its application to medicine. For example, when you do heart valves, or you try to study how to create an artificial heart, or what are the best characteristic of artificial hearts that we can create, you study the flow of blood through the heart, and you use really physics modeling of these fluids moving through your body, and you use mathematics to describe that. There is a grand vision that we are going to understand biology at the same level of which we understand physics and chemistry, so that we could write down a model for everything that happens in our body. And a lot of the genetics and genomics, very specific molecular data that we collect these days, is collected with the hope that they are going to be the ingredients for this big model. So far, we don't quite have that level of understanding. So we really use a lot of mathematics to do the statistic analysis of any hypothesis that we try to put forward to increase our understanding, and in cases like the one I mentioned, to describe some higher order mechanisms like the flow of blood in the heart. You do need quite precise mathematics to model that, and math. Another area that where we use a lot of mathematics is imaging. The way we do medicine has been completely changed by the fact that we can do CT scans or MRIs, and CT scans or MRIs rely incredibly heavily on mathematics and information theory in how we decode actually these signals and how we use them to reconstruct an image.
Okay, super. For those students who are interested in statistics, would you give any recommendations? Are there certain majors or certain courses that they should pursue once they enter college?
Yes. Well, I think statistics is a grown-up discipline in the sense that it really requires a lot of background. So I think the best thing to do is to start with a solid mathematics background, which you're already well on the way. But I work, for example, in an undergraduate major that is called Mathematical and Computational Science, and then it will change its name to Data Science, and it's effectively sort of a statistic type major. And we recommend our students to take 1 year of calculus and linear algebra. Linear algebra is particularly important for data science in general. So you need to be good at your integrations and derivative and have good linear algebra. Then I think any university will have a good course on probability, a course in mathematical statistics and applied statistics. Nowadays, if you want to do machine learning and really work with these high dimensional data sets, you are going to need some good competencies in computer science and in optimization. So there's many different ways, many different ingredients to work with data. And but you start with calculus, linear algebra, optimization, some programming, and then probability and statistics.
Okay, excellent. Yeah, any student who has understood all those subjects is well on their way to doing lots. Maybe I'll finish with one last question. I know you're at Stanford. Is that a photo of Stanford behind you?
Yes.
Some of our students here may be interested in going to Stanford. I wonder if you would say a word. Would you recommend they check it out?
Absolutely. Now, I am not going to say check out Stanford over UCLA. I've been at UCLA. I love UCLA. They are both wonderful schools. As a mom of two people that have gone through the college application, my condolences with you that you'll have to do it. But look at it as, really it's an adventure. Be bold in what you aim for, and don't suffer through the application process. Enjoy it as much as you can. It can be really a way for you to discover how great you are. You already are great, but sometimes it's good for us to tell ourselves, gee, I have done this and that, or, I had this difficulty and I overcame it, or look, I'm so interested in this topic. Wouldn't it be wonderful to go to a college and learn about it? So both the schools that you have here today are in California, which is a wonderful place to be when we don't have fires. Definitely apply to Stanford. I think Stanford has, all of these schools have this very scary, very low acceptance rate, but that's partly because so many people apply. And, this is one of the good things of the Common App or these applications online. Even if you have to do 2 or 3 of them, it's so much easier to transport the material from one place to the next. So everybody applies everywhere, and then you end up with this very scary small acceptance rate. But each of you has a very particular story, and it's going to be an excellent student, I'm sure, in any school you go. And every school would be very lucky to have you. You just have to make them know that's the case. You cannot expect them to know it to start with, okay? They don't know you. You know yourself. There are people that know you, can write you letters. Spend a little bit of the time and don't expect it to be successful all over the place. It is very much a random process in many cases. But know that any place will be very happy, very lucky to get you, and you just have to make a little bit the effort to let them realize that that's the case, so that they can give you the opportunity that they have to offer.
Okay, thank you. Good advice for all our students. I think we're just about out of time. So what I'll do is I'm going to turn the mic over to Maria. She's going to give a final remark. But thank you so much again, Professor Sabatti, and for all the previous speakers. It was wonderful.
Thank you.
I suspect everyone here probably agrees that the universe is written in the language of mathematics. Dr. Sabatti, we appreciate your presentation on probability statistics, machine learning, and now college recommendations. This is great.